All right, here we go. So now we're going to look at basically exponential growth and logistic modeling. Okay, so we're going to look at percentages and exponential functions, exponential growth and decay, that type of stuff. So at time equals 0, we say the population is at p sub 0. Okay, so if it's growing, let's say the town of Madison right now in the year 2023 is 7,800 people, and it's growing at 1% per year. Okay, so this would be times 0. 2023 would be times 0. Okay, so in 2024, if it's growing at 2%, you have to take the 2% times the 7,800 and add it on to the 7,800 that we already had here. Okay, so 2% of 7,800 is 156, plus 7,800 is 7,956. All of a sudden we have at year after 2024, then the next year, and so on. Okay, so what happens is the power becomes 1, the power becomes 2, the power becomes 3, and so on. So in the end, an exponential function is whatever you start with times 1 plus the rate times the time. Now, if it is exponential decay, this plus would become a minus. Okay, plus becomes a minus. All right, so if we're dealing with populations, okay, the population at whatever time depends on the starting population plus 1 times the rate to the time power. So, is this population growing or declining here? In this equation, is the population growing or declining? Growing. It's growing at a rate of 2.1%. It's growing at 2.1%. All right. The original population of the town or the city was 786,543, and it's growing 2.1% per year after that. Okay. Determine the exponential function with the initial value of 10 increasing at 5% per year. So we're at 10, okay? So the exponential function would be 10 times 1 plus the rate 0.05 to the time power. Well, we start with the rate that it increases to the time power, or 10 times 1.05 to the t. Okay? Suppose a culture of 200 bacteria is put into a petri dish and doubles every hour. Predict when the number of bacteria will be 350,000. Okay? So you start with 200. Okay? And then after 1 hour, you'll have 400. After 2 hours, you'll have 800. So it's 2 to the t times 200. And you set that equal to 35,000. Now, they say use a calculator to figure it out. Yep, you want to use a calculator to figure it out. What I would do is divide by 200 first. So it's 1700 equals 2 to the t power. And then they want you to use the graph and see where it hits 1700. Okay. As of right now, because we haven't hit the second half of the chapter, that's what you do. Okay. You take your graphing calculator, graph 2 to the x power, and make sure your window goes at least up to 1700. Okay. So you got to go wide a little ways, and then you'll get 10.77. Later in the chapter, we'll have an easier way of figuring that out. Okay. But using a graphing calculator, looking at graphs will help you out. Okay, modeling population. Okay. Compare the actual population to what we would predict that would happen. Okay. Now, When we do this, this is year 0. So 1900 would be year 10 and 20 and 30 and 40, 50, 60, 70, 80, 90. 1990 would be year 100. 2000 would be year 110. So if we started at 62.9, okay, 62.9 times whatever the rate is to the 110th power, we want it to equal 281. Now, let's figure out the rate for this first year and go from there. What's 76 divided by 62.9? Somebody on a calculator. 76 divided by 62.9. 1 point what? I need a couple decimals. 208. 1.208. Now, we hope that it's somewhere close to 281. Okay? If you take 62.9 times 1.208 to the 110th power, what does it work out to be? What does it happen to work out to be for this? And then I'll keep talking about it a little bit. Oh, so it's really, really, really big. Okay? So, this might not be the best way to do it. So, if you have your graphing calculator, okay, so I wish I could get out of this. Yeah, we'll discard it. Okay, I'm going to grab my graphing calculator. Oop, right here. Go to here. What I'm going to do is go into Stat, Edit, and I'm going to put the years in. I'm going to go year 0, year 10, 20, 30, 40, 50, 60, 70, 80, 90, and then put in the population of each of those years. So we got 62.9, 76, 92, 105.7. Oop, screwed that one up. 92, 105.7, 122.8, 131.7, 151.3, 179.3, 203.3, and 226.5. All right, so I got a bunch of numbers in there. Now I'm going to go to Stat again and going to go over to the right one to Calc. Now, this is an exponential regression is what we want because we're talking about modeling exponential regression. So if I hit enter here, I'm going to go list 1, list 2, and I'm going to store the regression equation. I'm going to hit vars, y vars. I'm going to store it in y1. So that way I can graph it later. Okay. If I calculate it, my equation is 66.66, and then times 1.014 to the x power. Okay. Now, this time, if we put 110 in there, I bet we're a little closer to 281. So I'm going to look at the graph of this. And I'm going to have to be pretty big here. I'm going to go change my window from -10, that's fine, up to 150 for the x's. The y's up to 500. There's my graph of my exponential rise of population. Now, what I want to see is I want to trace what the population is in the year 110. And it's about, according to our data, you should have about 309 million in the US instead of 281. So our exponential guess going on the data went up a little bit faster than what the actual population was. Okay? So that's using our graphing calculator. So plug everything in, get the equation, model it, and there we were. Okay? All right, the last one that we're going to talk about is maximum sustainable population. A population can't grow exponentially forever. Okay? The earth is only so big. Okay? So, there's at a point where a population flattens out. Okay? It can't grow anymore. That's called the maximum sustainable population. Okay? So, let's say a high school has 1,500 students and 5 of them start a rumor, and it spreads like that. Okay? By the end of T days, okay, how many people have heard the rumor? Well, how many have heard the rumor at the end of day 0, which is the first day of the rumor? Day 0. Well, e to the 0 is 1. 1 plus 29 is 30. 1,500 divided by 30 is 500 students already, correct? Okay. And then, if we put 1,000 in for time, then we can figure out how long it took for them. Okay. Oh, I said 500. Must be 50. 50 people at the end of day 1 heard the rumor. Okay. And then if you put 1,000 in there, it takes 4.5 days before 1,000 people have heard a rumor started by 5 people. Okay. All right. So what will your homework problems look like really quickly? They'll just ask at the start, is this growth or decay? And what would it be? Growth, because that number is what we look at. If it's bigger, if it's 1 or bigger, well, if it's bigger than 1, it's growth. So what was the percent growth? And it's going to be 11% because you have to move the decimal 2 places. Okay? So the exponential growth of this one would be, it's actually exponential decay. Exponential decay because r is less than 1. And it's greater than 0, less than 1. And then what is 1 minus 0.814? 0.186. So it's 18.6% decay. Okay. All right. And then filling these out, 5% is the original 1.17 because of 17% growth to the t power. Okay, so you'll have some like that. If we have a table, you put it in your graphing calculator. This is L1, this is L2, and you let the graphing calculator come up with the equation for you. Okay, let's do that once really quick here. Stat, edit. Now to clear out your list, go up, push clear, and go back down again. And that clears out the list. Don't push delete, because then that'll delete your list and then you can't use it. So it's clear, not delete. So if you go -2, -1, 0, 1, and 2, and then 0.61238, 0.89224, 1.3, 1.894, 2.75970. Okay. Once you get the numbers in, looking the way it is on the table, you push Stat, Calc, find exponential, hit enter, 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 and then I always store the regression equation into y bars under y1. And then push enter a couple more times. It gives you what you need. 1.2999 is 1.3 times 1.457 to the x power. Okay, so that's using your graphing calculator to figure them out. Okay, so you have some problems here. I will put them out for you.